Number one, so what we're looking here now is trying to figure out how we can look at centripetal forces with this idea of a banked curve, similar to what they have in NASCAR. So as you round the bends in NASCAR, they're not flat bends. If they were flat bends, we'd have to let the force of friction keep our tires sliding out of the curve. So when we have a banked curve, what we can do is try to ignore that force of friction and allow the normal force to provide our centripetal force. So we'll draw a free body diagram here so you can see which piece of the normal force is actually pointing in towards the center of the circle and how to calculate your safe speed to travel around a banked curve. So here's the free body diagram. Gravity is going to be down and your normal is going to be an angle like usual. But one thing we're not going to do this time is we're not going to tilt the plane. I know we've tilted the plane every other time to make sure that normal force was right in the y, but you'll see when we go through our derivation here that it's actually a little bit easier if we keep the xy plane up and down. Here's our bank curve, and you can see as the car drives away from us, the two forces acting on it will be the normal force and gravity, like we said. And if we draw a free body diagram this time, there's our normal force off at an angle, and here's our force of gravity straight up and down. If we keep the xy plane level, and like any other xy plane you've seen, what we can see is that gravity is straight down, and the normal is the one that's pointed up and to the right. And as you round this bend, as you change your direction, there's got to be an inward net centripetal force pointing in towards the center of the circle here. If we look at our normal force, you've got normal force in the y direction and normal force in the x direction. The force that's going to cause us to go in a circular motion is that x component. And the angle, if you use your geometry here, theta is the same as the angle of the hill. We can use that idea to solve for the centripetal force. We know that if you look in the y direction, gravity is going to be equal to the normal force in the y direction. And if we look at the x direction, the centripetal force is caused by the x component of the normal force. So we can go through a couple things and write some equations based off what we know. We know that force of gravity is mg, and we know the normal force here is going to be normal force cosine of theta if I look at that y piece that is straight up and down. In terms of the x direction was centripetal force, which we know as mv squared over r, is equal to the normal force sine of theta. So we have centripetal force equaling the x component, and we have gravity equaling the y component. Our goal here is to figure out the speed that we can safely go around here, and what we could do, since there's a normal force in both equations, one thing we could do is divide both of these. And cosine over sine gives us cotangent, so if I actually flip these and divide my x component over my y component, what you'll end up getting is tangent of theta equal to mv squared over r divided by mg. And since we have a fraction upon a fraction, we can simplify this and simplify it into getting rid of those and multiplying by the reciprocal here, which would give you just v squared over rg. Solving for velocity, velocity is going to turn out to be rg tangent of theta square root. So this right here is the safe speed that you can travel around the bend as long as you have a bank curve. You got your radius, you got your gravity, and the tangent of theta keeps you and maintains circular motion. But like this is showing us, what happens if we start driving too fast or too slow? One of your web-assigned questions will ask you this. And I'll throw up one of the scenarios here for you. If we're driving too fast around that bend, what you're going to notice is that your car is going to want to slide out of the circle. And if you start sliding out of the circle, it means there's a frictional force that's going to try and keep you on that hill and force you from not sliding out. Well, what you're going to have then is a frictional force that is angled as well as your normal force. Again, try and keep your XY plane straight up and down for this. And I know it might seem like a big pain, but the centripetal force is in this direction. So we can set any forces in the x direction equal to mv squared over r, which we again see as our normal in the x. And now there's a piece of friction in the x. So when you start writing your equations here, normal in the x and friction in the x will equal mv squared over r. But remember that your friction also depends on the normal force. So you can't just write the force of friction. You've got to actually find this hypotenuse to help you solve for the frictional component as you pull inwards. So if you're too fast, that's what's going to happen to the car. The car is going to try to slide out of the curve, and friction is going to try and pull back down and keep you in that bank curve. So you got more than one force keeping you in circular motion. Draw it again for a scenario where you're going too slow, and if you have questions on how to set that up, please come see me. And the last new idea in this section is this idea of center of mass. And the center of mass is just a point between two masses where you could imagine all the mass would be concentrated if you wanted to focus on these two objects as simply one object. So if you look at the two examples there, you can see mass 1 and mass 2. They are a distance apart, and if they're even masses, no surprise, the center of mass is right in the middle. However, if you start increasing one of the masses, that center of mass will shift towards the larger object. And the mathematical equation there is big M, which is total mass, multiplied by the center of mass, equals mass 1 times its x position, plus mass 2 times its x position. And if you had 100 masses, you could do this for a system of 100 masses. So let's do an example of trying to calculate where the center of mass is. And so in this example here, we've got two masses, a 4 kilogram object and a 1 kilogram object. They're separated by a distance d apart, and the question is, where is the center of mass? So it's not going to be right in the middle since they are even masses. And the way we can do this, remember that big M is the total mass, so that's really just 5 kilograms. We're looking for the center of mass position, so that's just x. For mass 1 is 4 kilograms, but its position is 0. So 4 times 0 knocks that out, leaves 1 kilogram at a distance of d. If we do our math to find the center of mass here, solving for x is going to get you 1/5 d. So it means about 0.2 times the distance between those two objects. So right around here is where we'd expect the center of mass, because it's closer to the heavy object than it is to the lighter object. So that setup for the center of mass in the x direction or y direction is real easy when you're just dealing with one direction. But we know that objects can be in 3 dimensions at once. The way you could write this up is that the total mass multiplied by the center of mass position would equal the summation of each position of each object multiplied by its individual mass. And that's what the little I there is for. You could put as many objects as you want and determine the center of mass for the entire set. Summations, when you add up the mass all the way along a certain length, like having a uniform rod here, you would have to add up each piece of mass for every little piece of length that you would move along this rod. It's the same formula that I just showed you. However, we're going to replace the summation with an integration. So you would integrate and add up all the pieces along the entire length of the track, dm, for each piece of the length there. We won't get into integrating rods yet until we get to further chapters, but if you would see this come across in a reading or something, that's what that means. And the reason you'd want to focus on the center of mass is if you look at this baton being tossed. As the baton is spinning through the air and these pictures were taken, you can see that there is a clear parabolic path. So if we just focus on the center of mass of the object, it actually follows all the kinematics and rules that we have for just single objects flying through the air. Same thing with this hammer. The hammer center of mass is closer to the hammer head. So you can see that black dot there. As it's tossed through the air, the black dot follows the perfect parabolic path, just like tossing a ball. So that motion about the center of mass, we can find the velocity about the center of mass. And we do that by taking the derivative of their positions. If you take the derivative of their position again, you get the acceleration of the center of mass. And if you focus on just the center of mass and any net forces acting on that mass, you can just follow how the mass accelerates from that central point. And the reason you want to focus on the motion would be something like this. There's a projectile fired up in the air, has a mass of 2m. As it reaches its peak, the projectile blows into two pieces. At that time, the back end of the projectile falls straight down, and the front end of the projectile moves a further distance forward. So if you look at that parabolic path and you actually calculated where it should go if it did not blow apart, you could go and measure that center of mass point and see exactly where the back end of the projectile landed. If you know that is the distance from the center to mass 1, if they're equal pieces, the other mass should be an equal distance from where the projectile should have landed. So that's why you can focus on center of mass. If things aren't nice, symmetric objects, then you can use center of mass and treat these oddly shaped objects as one point source.